and this is what we are gonna do. So I think you are seeing my screen. For this homework, you are gonna develop a file system. File systems are very complicated, but yours is going to be very simple. You will assume that you have a disk of size 1 megabyte. So you will assume that this is your disk. Okay, this will be your this is a regular Linux file. Okay, this disk is 1 megabyte. If you open a Linux file, okay, make it 1 megabyte long, and that becomes your disk. Okay, so your disk address byte 0 is here, and 1 megabyte byte is there. Okay, so it is up to you how to use this disk to store all the information about your file system. Okay, but as we said in the project, we said that you are gonna develop a file system that is Unix like. I am not saying that it's going to be exactly the same as Unix. I said it's going to be Unix like. So what do I mean by this? It will be similar to what we have shown you in the figure 4.9. Let's say this is our 1 megabyte space on our disk, and it is up to you. I mean, you need to design your file system, but you need to have some kind of a, well, I mean, in this case, maybe you don't need the boot block because you're not going to use a file system to boot your computer. Maybe you don't need this, but definitely you will need the super block. In your super block, you are gonna keep your system-wide parameters like the beginning of the root directory, the addresses of the inodes, the addresses of the blocks, and etc. Okay, then you will need your inodes, and the number of inodes that you gonna use is specified by part 2, and your root directory, and as you know, the root directory points to other directories, and it's so on and on. So you're gonna design this part yourself, and all of this information has to fit into this 1 megabyte file. Okay, so how are we gonna test your file system? We are gonna test it this way. We are gonna say that, okay, you need to implement. Okay, first this make file system program. It will say that it will be 4 kilobyte blocks, and I need 400 inodes. Okay, and then the name of the file. So the size of this file, my system dot, will be exactly 1 megabyte. So this will be an empty file system, but when I say empty, of course, it has all the super block defined, and it has all the inodes defined, empty inodes defined. So it doesn't carry any user related information, but it's a new shiny file system. And then in your part 3, you will implement this the program file system operations, file system oper. Okay, so it will take 1, 2, 3 parameters at least. Okay, first it will take the file system data, which is the same as this one, whatever it is. Okay, it will take it. So this is your file system. So this is kind of your disk. So it is very simple. There is no disk simulations, there is no head movements, and etc. For you to disk is just this file. Okay, your disk is just 1 megabyte long, and it is inside this file. And then your operation and the parameters. Let me give you a few examples. For example, if you say okay, file system operation, my file system data is this, my disk is this, and I am giving you a command. Okay, I am giving you a command, make directory. Okay, so what directory you like to do? It is under the root, it is user. Then under the user, it is YSA. Under the bin, YSA should produce an error, right? Because there is no directory named bin at the root. Okay. So these are all the operations that you need to do. Simple operations actually. This is ls. No parameters, just single ls. Okay. And it looks like we are, I don't know what happened. I mean, I didn't do, Ilhan, there is something wrong with these. I mean, there should be spaces here. Why don't we have spaces? There should be spaces between your...
Yeah, there is something wrong with the copying the text because of the Microsoft Word. I mean, you email me and I email you. It's
Okay, we will
confusing.
fix it. We will fix it. Okay.
Okay.
So this is the correct again. So this is the correct version here. So your program, your data, your operation, and your parameter. Okay. So I put these in the in quotes. I don't want them to be confused with the Linux files. Okay. And most of time what you're gonna do is you'll get a parameter and you will perform whatever it is. Sometimes you need to copy data from your Linux operating system to your file system, and in that case you need some Unix file, random Unix file, either 100 kilobytes long or 5 kilobytes long or 200 kilobytes long, doesn't matter. Of course, it cannot be larger than 1 megabyte long because your file system is at most 1 megabyte long. I mean, it is impossible to store this file there. And you are going to perform these kind of operations and see what kind of things you are getting. Okay. So you understand this one, right? This CMP. CMP is a unique command. In this case, what you are doing is you are copying a Linux file data, okay, a regular data to your file system, and you copying it back to your Linux system, and you are comparing these two. So whatever you have stored in your file system and whatever the original file should be exactly the same. There should be no changes. Ahmet Yasser has a question. In part 2, we say that we are going to create a file system that has 5 kilobyte blocks and we are going to have, yes, doesn't it the total of not exceed the... No, why? We talked about it, Ahmet Yasser, remember? If your if each of your file is 1 byte long, what does that do? Okay, doesn't matter. Okay, doesn't matter. I mean, you have 400 free inodes, and some of them are not usable at all. Okay. Of course, you should not allow any negative signs for the blocks or the free inodes, etc. And you like to do those kind of consistency checks, that's fine. Yeah, that's one block, that's true. Yeah, it might be that case, yes. I mean, if you think like that, there are many things that you like to check, but I didn't want you to be too specific about what can happen, what cannot happen. Okay. And if you like to make those kind of checks, that's fine. Okay. Any other questions? And you will submit three things. The first thing is your report in part 1. You are gonna tell us your design. Okay, you're gonna tell us how you define your directory and how you keep your free blocks and free inodes, your inode structure. Okay, inside your inode you keep your attributes and everything, right? And define your super block, what do you keep in your super block, and etc. Okay, this is a very important part of the project. The second part makes this make file system program, and it does this. Okay, and of course the numbers should be logical here. I mean that there cannot be any negative block sizes, or block size of 17 doesn't make sense. So you may restrict the users, saying that your block sizes could be only 1, 2, 4, 8, 16 kilobytes only, etc. Okay. And then in part 3, this one will take time to implement maybe, and you will perform all the operations. And some parts are bonus actually, like the linking, symbolic linking, and file system check. These are the bonus parts. Okay, and you may use these lines to verify your system, but you should test your system using lines many more than this. This is not enough. Okay, and we are going to test your file system like that. So you are going to submit at least 3 things. One is your report. Okay, the second one is your program for the part 2, and your program for part 3. Okay, if you like to use more than one C file and make files and etc. Okay, each one should be in a different directory, and then that's it. And if you like to put, Ilhan, why don't we make a list of what to submit? Okay, do we have it? What to submit, homework is done. Okay, so we will make a list of what to submit, and let's get them. Okay, they should submit at least one file system data. So we need it. Also, we need a txt file that contains commands, file system commands. Just an example one, just to see, so that we don't run into problems like the I use it this way or that way. Follow the strict instructions. Okay, don't make any changes to the parameters or the order of the parameters, that kind of stuff. Otherwise, we cannot test your system. And whatever you do, it should work on this virtual machine. Okay, we are going to test this on this virtual machine. Okay, any questions?
Sir, I didn't get the answer of my question. Can you repeat it again, please?
I said that if you like to make those kind of checks, saying that this is not possible, that's fine. But if you like to go that way, there are many other things that you need to be checking. I don't expect you to check all the impossible stuff. That's what I am saying.
So we can store files in units less than a block if you want to.
How are you gonna do that?
Because like that means that we can store stuff in less than blocks, like
You,
half a block.
with the I know structure, it is not possible. How are you gonna do that?
No, not with the inos, for the data blocks. Like I can have 1 kilobyte
Each
or
each
10
I
bytes data.
node each I node can point to a data block. You cannot point to a sub data block. With the I know structure, you cannot have a file. I mean, the file size could be 1 byte, but the position that it occupies in the file system is at least one inode and at least one block. So it's going to be at least, if your block size is 4 kilobytes, 8 kilobytes.
Yeah, then it's impossible for us to give the parameters 4 and 400 because it exceeds 1
That's
megabyte.
what I said. I mean, I keep repeating the same thing. Okay, it might
Okay.
be impossible for that number. Okay, but it is okay to have 400 inodes on your file system. At the end, some of them may not be used at all. Okay,
Okay, I see. Thanks.
and I mean, it doesn't work that way actually. I mean, sometimes some of your inodes might become unusable in the real life. Okay, so you want to keep some extra inodes around. Okay, so this happens. I mean, sometimes you reserve more than enough inodes on your file system. Okay,
I understood. Thanks.
Ilhan, I don't know what happened. I mean, why do we? Okay, let's fix these issues. I mean, there are many. Okay, let's go over the homework and let's put these spaces back.
Okay.
Okay,
I think my office is my office has problem.
okay.
I
So
contact
we
them.
will fix it. Hmm.
Okay, okay, sure.
Good. Um, okay, let's go back to the lecture if there are no questions. So we were at the input output. We were discussing our input output devices, and we said that okay, input output is important. Okay, we need to, as an operating system, we need to manage our input output devices and input output operations. And in fact, we said that most of the operating system code belongs to the input output processing. Okay, your kernel, your scheduler, for example, is small. Your virtual memory management is code for those is small. They are important, but they are small. Also, your file system, you're going to write a file system, and you will see that it is not a very big, complicated piece of software. So, but when it comes to the I/O, it is not that complicated, but it is lots of code because you need to deal with lots of different devices. We talked about it, and we said that we will talk about the principles of I/O hardware. Why we talk about it? Because although we are not going to design any hardware in this course, we need to know its details so that they can be programmed. Then we will look at the principles of I/O software, and then later we will start talking about the individual input output devices starting from the disk hard drives. Okay, so we talk about these. By the way, yesterday some people have asked me where are those controllers and that kind of stuff. This was our simple picture. We said that we said that this is our CPU. They are all connected to the main system bus, our memory, and the video controller. And some people had asked me where are the controllers on the main board, and this is directly from the Wikipedia. This is directly from the Wikipedia. On the left, this is your architecture of your main board, main system architecture. At the top, I have the CPU. Okay, the CPU is connected to this North bridge. which is connected to the fastest bus in your system, your memory bus, which is connected to your memories, and your high-speed graphics bus. So your memory and your graphics card is very special. You need to communicate with them in a very, very fast way. So where is the controller for the graphics card? Of course, graphics card controller is in the North Bridge. Okay, it is in the sometimes it is in North Bridge. Sometimes, I mean, if you are using the onboard, if you are using the onboard graphics card, it might be in the North Bridge. But if you are using an external graphic card, then your controller is in there, right? And then we have a internal bus, second bus, slower bus, and you have your south bridge. Connected to your south bridge is all of your hard drives, your Ethernet, your audio stuff, and etc. Okay, and most of your controllers are here. IO controllers are there. And then you have another bus, LPC bus. Okay, your serial ports and your parallel port floppy disk. Slower devices are connected to this bus. And again, controllers are in the south bridge. And this is an example board. This south bridge, maybe red, south bridge and north bridge are the two important chips, and we call them chipsets. They are important. They are, in terms of performance of your system, they are as important as your CPU. Okay, and these are conveniently connected to your memory slots in North Bridge. Also your PCI Express, slot. Okay, is here. This PCI Express where you connect your graphics card is connected to North Bridge. Slower devices like the PCI ones, they are connected to your south bridge. Okay, just study these from Wikipedia, other sources, and you will understand them better. So, I mean, this is how we show you, but in reality, this is what happens. Okay, but the ideas are the same. Ideas are the same. So study this picture carefully. Okay, then we talked about memory mapped I/O and I/O port space, and we said that both of them have advantages and disadvantages. We talked about them, and then we said that direct memory access is an important hardware feature of our systems, and we talked about it with direct memory access. And direct memory access, programmed I/O interrupts, they are all used together. There are sometimes alternatives and they are sometimes used together. We talked about this. And we looked at the sequence of operations that we do with the direct memory access. Okay, direct memory access. So I think somebody has asked me, where is my DMA chip? Usually on our modern operating systems, modern architecture, each device has its own kind of DMA. Each PCI device, exactly. Okay, so your hard drive has its own DMA chip. Okay, so then we talked about the interrupts, and I think that's what we were doing with the last slide in yesterday's picture, yesterday's lecture. So we said that interrupts are the main way of communicating with the peripheral devices. Without the interrupts, we had to do busy waiting. We had to always check if the data is ready with our peripherals. That would make our life a lot difficult, a lot inefficient. because you're wasting your CPU time. With the interrupts, things are better. The interrupts are much more efficient in terms of CPU time than the busy waiting. But interrupts are not cheap either, and because every time an interrupt happens, you need to do context switching, and context switching is expensive, and we talked about it. And we are gonna see a few more examples. Okay, so this is mainly what happens with the interrupts, and we are gonna see more detailed operations about the interrupts. Whenever a IO device finishes the work, for example, I loaded some data from the desk, or your byte from the keyboard is ready, that device causes an interrupt on the bus, okay, system bus, okay, and the interrupt controller detects that signal, and interrupt controller says that, okay, I see that there is an interrupt happening, and I will inform the CPU about this, and it informs the CPU about this. CPU stops whatever it is doing, okay, and this is all done by the hardware, okay. This step, and this step, they are all done by the hardware. The operating system is not involved with raising the interrupts or informing the CPU about the interrupt. This is all done by the hardware, and you know the details of it from your architecture course. And when the CPU knows about the interrupt, okay, it says that, okay, I'm going to handle this interrupt. Then after that, operating system comes in. Okay, operating system comes in. When does the operating system come in? Operating system comes in when our interrupt procedure is called, and we're gonna see it in a few minutes. Okay, so before the operating system start running, hardware always saves certain information before starting the service procedure. Okay, the hardware saves very basic stuff like the PC, of course, program status word, only a few critical registers, not all of them. Okay, just a few of them, very necessary, very crucial ones. And after that, it is up to the operating system what to save about the state of the CPU, state of the system on appropriate places. So it is the operating system's decision to make to those kind of saves. Okay, so we will come back to the interrupts again, but before going there, let's look at some of the issues. Sometimes, I mean, raising an interrupt, handling an interrupt seems simple, but sometimes it is not that simple actually. I mean, our current architecture is pipelined, heavily pipelined. A simple pipeline like this, three-stage pipeline, but most of the time our pipeline structure is like on the right. A superscalar CPU. You have more than one pipeline at the one end, fetching and decoding units, and each one can do fetching and decoding in parallel. Okay, and you're holding buffer, and you have many execution units. So at a given time, when the interrupt happens, you might be executing 1, 2, 3, 4, 5, 6, 7 instructions at the same time. Okay, you might be executing 7 instructions at the same time. Okay, so it might look like this. Okay, let's say address number 328 contains an instruction, 24 another instruction, 20. Okay, so I am executing maybe 1, 2, 3, 4, 5, 6 instructions, and some of them are at the beginning of the execution cycle. Okay, some of them are at the very near end. When the interrupt happens, so what am I gonna do? Should I save all this information like this to some place, or should I do it this way? Should I say, okay, I am going to clear out all the instructions in my pipeline, so I will never leave some of the instructions unexecuted, some of them are executed. Okay, so if you prove it this way, this is called precise interrupt. You definitely know which instructions are executed fully and which instructions are not executed fully. Okay, so either executed or not executed. So this looks like nice solution. You wait until all of your instructions are executed. Nice enough solution. So you have only a minimal set of information to be saved on your stack. So what is the problem with this approach? I said it is nice, it is clear. What is the problem then? I mean, as always, if there are two ways of doing something, then there should be a trade-off, right? I mean, like good things and bad things. I told you the nice thing about precise interrupts. It is nice because when the interrupt happens, your pipeline is cleared. All the instructions, they are all executed. So all you save is my program counter is here. I am saving it. And I know that before that everything is executed. After that nothing is executed. That's what I save. As opposed to this one says that my PC is here, but I know that some of the instructions are halfway executed. Some of them are very, very little executed. Some of them are almost executed. I need to save all of this information. And it is a complicated information actually. It is not easy. So what is the problem with part A, precise interrupt? Instead of dealing with imprecise interrupts, I just only say minimal information, and restarting the process is easier that way too. Anybody? Yeah, exactly. Selman says that maybe waiting for the instruction is slow. I mean, when what is the point of interrupts? As soon as something happens with the hardware, CPU is supposed to take a look at it, right? If CPU is waiting for the whole pipeline to clear out, the CPU has to wait all of those 7 instructions to complete their executions. Then you are going to be late to handle some of the you are going to be late to handle some of the interrupts. That's one thing. The other thing is that if you clear out the all the pipeline, that's going to take time. Also, when you restart your process, filling in that pipeline is going to take another long amount of time. So although A is simple, it might be inefficient in terms of CPU performance and handling of the interrupts. So sometimes they prefer using B. Although it is more complicated in terms of hardware, it is more complicated in terms of operating system tasks, it might be more efficient at the end. Okay, imprecise interrupt. So for the precise interrupt, PC is saved in a known place. I know that. All the instructions before the PC program counter is executed, and no instruction beyond PC has been executed. I know that, okay? And sometimes I need to, instead of executing them, sometimes I need to undo whatever effect they had. This is precise interrupt. And imprecise interrupt, okay, when the interrupt happens, um, the CPU dumps lots of data on the stack, and it is the task of the operating system to sort out the details of that information. And the code to save that information is complicated. Also, the code that is required to restart the program, restart the process might be complicated. Okay, but again, we cannot say that one of them is better than the other one because they are all preferred depending on your system. Okay, so that was a small instruction to the small. That was a small introduction to the hardware components of the input output. We talked about the interrupts. We talked about DMA, right? And we talked about the controllers. Let's look at the software side of the I/O operations. Okay, so the goals of the I/O software is simple actually. You will say that whatever I/O software you have, it will be preferred to be device independent. Okay, uniform naming is a form of device independence. Okay, let's look at both of them: device independence and the uniform naming. As the name implies, device independence is okay. Um, as a programmer, I don't need to know the details of the storage that I am accessing to. Whether it's a USB or CD-ROM, doesn't matter. I use the same operations. Okay, so I don't have to say, okay, I am accessing a CD-ROM and so I am going to use a different procedure. Okay, and in fact, in Unix systems, as we have mentioned many times, if this is your root directory, and then you have many other directories, one of the directories is the mount directory. Under this you can mount your USB disk, your C drive, D drive, or your CD-ROM. And under these directories you have your regular files. I mean, your program doesn't know that it is working on a USB drive or the hard disk or the SSD. Okay. Related to the device independence, your naming of the files should not be any different. Okay. So your file names for a USB drive or the hard drive should not be different. It should be exactly the same. Remember the extensions, CD-ROM extensions for the Linux file system. They added new fields so that I can have Unix-like names for my CD-ROM files. So that's for uniform naming of the CD-ROM files. And the error handling should be done without telling most of the time anything to the end user. Okay, we know that most of the time I/O devices are mechanical devices. Okay, if something happened, for example, when I am loading a block from my desk, if there is a mechanical problem, I could not do the seek. I couldn't move my head to the desired position, so that's an error. But I should be able to handle that error as an operating system without telling the user, saying that there is a head movement error. So try it again, do the recalibration, do something else, solve the problem, and bring the data to the user without telling the user. Of course, there is a very serious problem. What are you going to do? You cannot do anything, but most of the time there are things that you can do handling the errors. Let's say you loaded a file from the disk and you check some turn out to be bad. So what you're gonna do? you're going to try it again and try it again until you load the file correctly. So error handling should be handled, should be done without upper levels even knowing about the error. So three things, three common goals of the I/O software are this. Then we have synchronous and asynchronous transfers. Most of the physical I/O is asynchronous. What do we mean by this? The CPU starts the transfer and goes off to do something else. Okay, so I am blocked with the um, um, with the synchronous operations. What do? I just issue my command to the operating system. When the operating system makes the data available, I wake up and I continue. This is called synchronous. With the asynchronous operation, I mean, remember, we are talking about in terms of user, okay? Users don't know anything about the interrupts, okay? Users doesn't know that there is an interrupt happening, and whenever I am blocked, I am waiting for an interrupt to happen, and etc. Sometimes, for some systems, these interrupt operations are made available to the end users. Some operating systems make asynchronous I/O available to the users due to the performance issues. Okay, so usually, I mean, remember when you use your, let's say, write function in C, your program is like you write a file, you write some data to your file, and after the write you continue, right? So you don't know that you are blocked. I mean, even if you know that you are blocked while you are writing it, you don't do anything else. With the asynchronous operation, interrupt-driven operation, when you say write, the operating system immediately comes back to you, say that, okay, I have scheduled a write operation for you. You may continue doing some other stuff. And when this write is complete, I will inform you. So it lets you know about this whole operation. Okay? So synchronous, and most of the time, as I said, most users are doing this blocking transfers. When I do a write, I know that I'm going to be blocked, and that's fine. Doing an asynchronous transfer as a user, as an end user, is not easy. Of course, at the bottom of the things, I know that everything is done most of the time with the interrupts. Another issue with the I/O software is the buffering, which is very important. Okay, which is very important, and we will talk about it. The thing is that whatever you read from your hardware cannot be stored directly in their final destination. That has some problems. I need to keep copies of the transferred data, and we are going to see examples of it. Okay, this is one example of a using buffer. One example of using buffer. Let's say I have a text to be printed to the printer. So I make a system call. Okay, say that print, and I give this address of this buffer. So what I do is I copy this buffer to my kernel space, and then in that my kernel space I start printing them. And there are many ways of doing this printing operation. I can do busy waiting polling, I can do interrupts, or I can do the DMA. So I am going to look at each operation one by one. Okay, first I will do the most inefficient and maybe simple to understand one, which is the polling or programmed I/O. Then we are going to look at the interrupt driven one, and then we are going to look at the DMA. Okay, let's look at the programmed I/O first. Okay, so this is directly from the book, polling or busy waiting program.io. Okay, so whenever the user says that print this buffer, okay, this is operating system code, this is kernel code. The user says that this is the user code, print buffer, and what else, print buffer and count. That's what the user says, print this buffer, this many bytes. Okay, and when you get that system call, this is what the operating system do. It says that, okay, I will first copy that buffer to my location, this many numbers. Okay, so it will start copying that buffer to the kernel. It doesn't start working on the user's buffer. That's dangerous. Why? Because I mean, the picture is this. There is a buffer here, and it is A, B, C, D. Kernel doesn't want to work on this green box. Kernel says that I will copy everything to my kernel space. This is much safer. So what would be the problem if the kernel works on this green buffer while it is printing it? Can you give me an example problem that might happen? If kernel works on this one, I mean, without making a buffer, without making a copy of that buffer. Maybe I should let's delay this question. Let's look at the code. Then after that, I will come to that question. Okay. So first, I will make my own copy. Okay, my own copy. I will copy from buffer to my P. Okay, this is P. This is buffer. Okay, I'm waiting. So synchronization problems. Buffer and P. Then okay, make this copy. Then I have a loop from 0 to count how many bytes I am going to write. In that case, I think it was 8 or something like that. And there is a busy loop there. Okay, it says that if the printer status register, it looks like this printer status register is kind of an address, right? It's an address. So I am doing a dereferencing it. If it is not ready, then I will wait in this loop. It's an infinite loop. See, it is using memory mapped IO, right? Memory mapped IO. So if this is my memory, at the top of my memory there is a pointer. The name of that pointer variable is printer status register. Okay, whenever I access this one, okay, whenever I access this address, okay, whenever I access this address, it will tell me either it is ready or busy. If it is not ready, then I will wait. Okay, if it is not ready, then I will wait. If it is ready, then I will copy my my byte located at index number AI to this printer data register. Remember, in our system, let's do this. This is my CPU. our architecture, and this is my printer controller, and inside my printer controller it looks like I have two registers. One of them is printer status register. The other one is printer data register. So this is printer status register, printer data register. Okay, and I need to access these two registers so that I can print out my characters one by one, and these are connected to the system bus, and here is my memory. Okay, so it looks like I am using a memory mapped IO. So this programmed IO is using the CPU time all the time, and CPU spends very long amounts of time because printing each character might take a few milliseconds, and a millisecond is a very long time for a CPU. So I am wasting all the CPU time to print a few characters. Instead of doing useful work, I am doing this. Okay. So I have a few questions. Doğancan says that can this kernel code be interrupted? Yes, I mean there are some kernel codes are not interruptible. You just disable interrupts. Some of them are interruptible. It looks like in this case there is nothing wrong about being interrupted. Well, I mean this one doesn't use any interrupts at all. I mean maybe interrupts are not available, but I mean as a general answer to your question, some of the kernel codes are not interruptible. Some of them are interruptible. And Yusuf has a question. There is no additional register on device that specifies command. Well, I mean, no. Printers are much complicated than this, Yusuf. Printers are much more complicated than this. It doesn't just have two registers. Of course, they have. They are much more complicated than that. And most of our printers are actually computers. Okay, they can execute. They have, you know the PostScript, right? PostScript language. They can execute the lines of that language. So they have interpreters. They have their own memory management and everything. They are much more complicated than this simple structure. Okay, so in this case, our printer is very simple. Whatever data you put into printer data register, it is printed. That is as simple as that. Okay. So as we said before, I am not going to go into the details of how the hardware devices work. This is simple enough. So we leave it that. Okay. Oh, it looks like I am out of my time. Uh, if there are no other questions, let's take 10 minutes of break. And after the break, we will come back, and as we said, this is too inefficient. Why don't we use the interrupts? So we go to sleep, and whenever the printer is ready, we handle it that way. Okay. So we are going to write another kernel code that uses the interrupts. So 10 minutes of break. We will come back at 11:36. Okay, see you in 10 minutes, and your attendance is ready. Thank you, Ilhan. Okay, so let's look at the interrupt driven program. Oh, Ahmed, regarding your question again about the 400, for where is Ahmed? Okay, 400 free inodes. Ahmed, you had a question about 400 free inodes. Sometimes 400 free inodes is needed. Suppose you have 400 files, okay, hard linked to the same 1 kilobyte file, okay. So you need 400 inodes, but on your data block you just only need 1 block. So these kind of things can happen. Well, even though the hard linking or soft symbolic linking is not in the base project, but if you do the optional part, you may end up using all of your free inodes, and while you have lots of space left, okay. Yeah, so it could happen. You understand, Ahmed? Okay, so let's go back. Let's uh, let's uh, look at this program.io again. So we looked at this, and this is the kernel code, and this is what we say. If each character takes 10 milliseconds to print, and then lots of time, that's like 10 milliseconds, like an infinity for CPU. You could do many things in that time. So maybe 10 milliseconds is enough time for us to context switch and do another useful work and use interrupts. And this is our code. Again, the user says that print, this is kernel code part 1, and this is kernel code again part 2. And the user says exactly same thing. Print buffer count, and this is the system call. Okay, it says that copy from the user from buffer to. Oh, okay. We forgot about something. Remember what we said? I had a question. Why do we have to copy? Why do we have to copy this buffer to this location? Why do I have to copy this buffer in my user space to my kernel space? Wouldn't that be the same instead of doing this, do this? Buffer I. What is wrong with this? Instead of pi, what I say, buffer I without copying. This would be more efficient because I don't have to copy. I don't need the space. I don't use the CPU time for copying. Maybe others can use it. What others? Who are others? Do you mean the others can use this green buffer? This is my user space. I am the only one that use that buffer. I am protected from the others. I mean, which space is more valuable? This space, green space, or the black space? Of course, the black is more valuable because it is inside the kernel. And if you like to save some space, save it from the kernel because kernel space is more important. It has something to do with the virtual memory. I think we talked about this. Yusuf, you have to explain it. Since we are using memory mapped IO, So what? Doesn't matter. No, it is possible. I mean, this is buffer I is in my address space, and this is memory mapped. No problem. Maybe buffer is overwritten. Why would it be overwritten? It is. I mean, that green buffer is in my address space as a user, and if I don't overwrite it, I should be fine. Yeah, Furkan, you have a point, but you need to explain it. Why would it be overwritten? As a user, I am not changing it. As a user, I issue this command, right? As a user, I say that print this buffer, that's it. And after that, I wait until that buffer is written, right? I am blocked. So nobody is going to overwrite that buffer. But you, as I said, you have a point. I don't. Mustafa, why don't you use your microphone? I don't know what for flashing, and is that a question? No, Yusuf. I mean, it doesn't make kernel. I mean, in the kernel, you're the operating system kernel. You have. I mean, if I can do this as a kernel, check this out. Okay, if I can do this blue part, I should be able to do this the second blue part too. They are both doing the same thing. They are accessing the user's data from user space, right? I mean, just if you look at the contents of those two blue areas that I showed you, they are exactly the same. They are accessing the buffer of the user, both of them. I mean, instead of doing the copying at the beginning, I am doing the copying one by one. Mustafa, I don't understand. I mean, I mean, how am I gonna, is that an answer? Buffer flushing? We don't do this because buffer flushing? I don't understand that answer. Either just explain it or Furkan had a point. He said that the buffer may be overwritten. But as I said, okay, this is what I issue as a user. I give this green a command, and nobody is going to override it. But remember, I am using I am using I am using virtual memory. Okay, after I issue this command, after I issue this command, it's going to take a while to print that data, right? So my process is blocked, right? My process is blocked for a very long time until the data is written to the printer. Since my process is blocked, the operating system may decide that my pages of virtual memory is not being used. So it may swap out my pages, and the operating system may swap out this part of the red part of the virtual memory. Okay, so If that part is swapped out, then in that case, this loop that I have modified that directly prints the buffer is not going to useful. Okay, so the problem has something to do with the virtual memory. You cannot be sure that that buffer is always available to the kernel because it may be swapped out. You may say that maybe I can lock my page so that it is not swapped out. That makes it more complicated. So usually, whenever a kernel needs some data from the user space, it copies it. It makes another copy. Okay, so this is an important point. Just keep this in mind. And this makes a nice exam question actually. Why don't I make a note of it? Exam questions, yeah, okay. 5.8, yeah. Why? Okay, good. So let's go back. And let's go to the interrupt version. This is the interrupt version. The user said that, okay, print this buffer. First, I started by copying it. Doesn't kernel access with the user's address space? Yes, that's true. So you mean that I keep using that page so that the operating system would know that that page is being used? But remember, this loop is going to take lots of time, 10 milliseconds, and within 10 milliseconds, your pages might be swapped out. For this example, if this loop takes more than a few milliseconds, okay, it might take even more. So that's going to be a problem. So usually kernel routines they don't risk these kind of problems. Okay, they don't risk this kind of issues. They just copy everything from the user space to the kernel space. Okay, so the user said that, okay, print this. First, I copied my buffer to my kernel space. Then I enabled the interrupts. And I said that I will wait until the printer status register is ready. There is a busy loop. Whenever it is ready, I will put my character first, and then I will call the scheduler. I will tell the scheduler that, okay, this process is blocked and schedule something else. Okay, this is the first part of the kernel code. This is the interrupt handler. Whenever the printer says that I am ready to print something, okay, inside this interrupt handler, first I check the count. If the count is 0, then that means that I have printed everything. I unblock the user. That means that the user doesn't have to wait anymore. Otherwise, if the count is not 0, then I would put the character number I to the data register. I would decrement count number 1, and I would increment I by 1. And I say that, okay, I handled the interrupt, and I would return from the interrupt. So this one will be called how many times? How many times this part of the code will be called on the right? Part B of this code. How many times this one will be called? the code in part B, how many times do you think it will be called? To print a buffer. Length of the string, yes, that is the count. Exactly, it's count times. It will be called count times. Okay, it will be called count times. But the part in A will be called just once. Okay. So yeah, Doğancan, Yusuf, and Furkan, you are all right. You are all correct. Okay. So the part A will be called only once. Will be called only once, and part B will be called count times. So that's good. So that means that there will be count times context switches, and context switching is expensive. Context switching is expensive. But if it is not as expensive as waiting in this busy loop, then I am better than this programmed IO. I am better than programmed IO. Okay. So again, interrupts is more efficient in terms of CPU time. My CPU can do other stuff while I am waiting for the interrupt. But they have some their own inefficiencies in terms of context switching. Okay, so to prevent this context switching back and forth again, what do? We use the DMA solution. Okay, we use the DMA solution. Let's look at the DMA code now. Okay, of course with the DMA you need a DMA controller. Okay, the DMA controller feeds the characters to the printer one at a time without the CPU being bothered. Okay, so this is a very nice sentence actually, this one. I like this a lot. Okay, in essence, DMA is programmed I/O, but instead of CPU doing the work, DMA controller doing all the work. DMA controller checks the printer registers. If they are ready, just transfers the data. Okay, so the biggest advantage of DMA is it doesn't use CPU time. It doesn't use the context switching for the CPU. Okay, so it's a win-win situation. So what is the downside? Of course, I need the hardware hub with the DMA. I need the hardware hub. So let's look at the code. Code is very simple. Part A is, okay, copy the data from the user space to the kernel space, and I set up my DMA controller saying that, okay, you are gonna transfer this many bytes from this buffer space to the printer's registers, and I will sleep. Okay, and whenever DMA does that, it causes an interrupt, and I acknowledge the interrupt, I unblock my user, and I return from the interrupt. So the part A will be called only once. How about part B? How many times is part B going to be called? The operating system would call the part B how many times again? Just once, exactly, just once. Because whenever the interrupt happens, that means that who causes this interrupt? DMA causes the interrupt. DMA says that I am done. It is not the printer. It is a DMA. Okay, it is a DMA causing the interrupt, saying that whatever you have told me, it is done. Now you are unblocked. Okay, so good. So DMA is as efficient in terms of CPU time. It is very efficient, more efficient than, of course, programmed I/O, more efficient than the interrupts, and it is fast too. Okay, good. So we looked at three software solutions that use some hardware hub to do some input output. Good. And we have seen examples of using memory mapped I/O, and we have seen examples of using interrupts. Good. Okay, so let's continue our discussion with the I/O software. These are the layers of the I/O software. Of course, at the bottom I have the hardware. Hardware is not software, we know that. On top of it, at the lowest level is the interrupt handlers. In your kernel, okay, you have your interrupt handlers. And we have written two interrupt handlers. One is here, okay, this is the interrupt handler. And the second one is here, another interrupt handler. These are very low level I/O software pieces. Interrupt handler. On top of the interrupt handlers, I have the device drivers. What is a device driver? Device driver is the software that communicates with the device controllers. So they act like a interface between the operating system and the device controller. And we will talk about the device drivers in more detail. And on top of it, I have device independent operating system software. Device independent operating system software. This part of the I/O software doesn't know much about the hardware because all the hardware related stuff are isolated downwards. Device drivers make these isolations for you. If I have a USB device driver for my USB stick, and if I have a hard disk device driver for my hard disk, okay, their interfaces to the user is the same. Opening a file, closing a file, creating a file, deleting a file. Although at the end on hardware, on my interrupt handlers inside the device drivers, things are very, very different, but as a user of those device drivers, I would see exactly the same thing. So that's why I would say that this layer of the operating system, device independent operating system, it doesn't know much about the hardware, I/O hardware. Okay, that's why it is device independent. Doesn't matter for that part to have a USB file or a hard disk file. Okay, and at the top I have the user level I/O software. That means that I/O software that doesn't run in the kernel mode. Okay, maybe up to this point, this red point, everything is in the kernel. Maybe draw it better. Okay, so this part is in the kernel, and this part is a user space. And even inside the kernel, there is piece of code that is device independent. Good. So Yusuf, and it's a great simplicity, but also limits the features of devices, I guess. Simplicity to the user, of course. Yusuf, are you talking about what? You are talking about the device independent operating system part? I guess so, yeah. Okay. Okay, so we are going to look at the layers of the I/O software one by one, starting from the interrupt handlers, device drivers, and device independent stuff. Previously, we have looked at the interrupt handlers previously, but that was for the hardware side. Okay. Now we are going to look at the interrupt handlers in terms of software. Interrupt handlers in terms of software. Let's look at interrupt handlers. Okay. So typical steps after hardware interrupt completes. Okay. Hardware interrupt happened. Remember we talked about it. Whenever it happened, hardware saves some important CPU information like the program counter and the program status word and etc. And after that, it calls the operating system. Okay, it says okay, here control is yours. I said some minimal stuff. Now control is yours. After that, software operating system software starts running. So this is what it does. Typical steps after. Okay, this is important. Typical steps after hardware interrupt completes. Let's make this comparison with the hardware part. Okay, hardware. Okay. When we talk about the interrupts, okay, this is what happens when the interrupt happens first, and this is all handled by the hardware. When the IO device finishes its work, it causes an interrupt. An interrupt controller detects this interrupt, and it informs the CPU about this interrupt, and the number of the lines is used as an index into a table called interrupt vector to fetch a new program counter. So this part this part is the last thing that the hardware does. Okay, say that I save some minimal stuff. Now I get a new address from the interrupt vector, and I will jump to this address, and this address specifies the operating system interrupt handler. Okay, we don't have a single interrupt handler. We have different interrupt handlers for different interrupts. That's why we have an interrupt vector. So that thing is chosen. Now I go to software side, and the operating system says that hardware gave me the control. Now I'm going to do this. First, I will save all the information about the CPU. Save registers not already saved by the interrupt hardware. Okay, all the registers that are important. Also, I like to save some memory management related stuff. So, and then I will set up my own stack. Okay, set up my own stack, set up my own context, like the memory management tables and etc. So this part will take some time, because setting up the context for the virtual memory management, TLBs and etc. is going to take some time. It is expensive. And after that, I will tell the interrupt controller that I got the interrupt, I am handling it. So you are free to handle other interrupts. So I send an acknowledgement signal to the controller. And then remember, I was running a process. Okay, and this process has stopped. I need to update the process table entry with all the required registers and etc. So that whenever I come to that process, everything is ready for that process to start up again. This is step number 5. Then step number 6, run the interrupt service procedure. I already know its address and everything. Okay, and extract information from interrupt devices control register. I mean, depends on what kind of interrupt happened. I mean, if it is a printer interrupt, printer says that I am ready, I don't have to extract any information from the printer. But if the mouse says that I have some data for you, then I need to get data from the mouse. Okay, then after I handle, so this is the step number 6 is the reason why we are running this interrupt. Okay, But before we do that, we have to prepare some context. We have to do some preparations. Then after number 6, step number 6, I don't have to uh, I don't have to do anything. I don't have anything to do anymore. So what am I gonna do? I need to go back. Okay. So I need to go to the scheduler and choose which process to run next. It is either the same process that I have interrupted or something else. Then I set up again the MMU. I am setting up the context again for a new context switch, and I load everything from the process table entry and start running the new process. Okay, this is what happens. This is what happens when the interrupt happens. So we looked at two sides: the hardware side and the software side. Okay, I guess I have a question. What is the difference between step 1 and 5? Step 1, save registers. Okay, step 5, step 5 copies necessary data to the process table. That will include the register information and etc. Okay, step number 1 kind of says the CPU state, when this interrupt had happened. Interrupt might have happened while I am running a kernel piece code. Okay, so when the interrupt happens, I might be in the kernel mode already. So step 1 always happens. Step 5 may not happen all the time because I may not be running any user level processes. Okay, and there might be other things to save into process table of the process, like the memory management related stuff. Good question. So this is what happens with the interrupt handling. Good. So let's go back a little bit. Remember, this is the IO software layers. We looked at the interrupt handlers. This was the lowest level of the IO software. On top of it, I have the device drivers. And of course, device drivers, they know the devices and they know how to handle. They know how to handle the interrupts regarding to those devices. Okay, so device drivers, they include lots of interrupt handlers regarding their devices. So let's look at a little bit device drivers in a more detail. And this is the picture. Again, I have my physical device at the bottom. I have a controller, an electronic component that acts like a interface between my computer and the device. And the driver is the part of the operating system. Driver is the part of the operating system. Of course, it's a software. Part of the operating system that knows the details about the controllers. Okay, that knows the details about the registers inside the controllers. And the rest of the operating system, they talk to the drivers. They don't talk to the controller. Okay, so rest of the operating system, remember I showed you this is an interrupt handler, right? Figure 5.9b. This part B, is an interrupt handler. This interrupt handler is part of the printer driver. Okay, this interrupt handler is part of the printer driver. Again, this one is part of the printer driver. Although I am not handling any interrupts here, I am directly accessing the registers of the device, control device. So this has to be part of the driver. Again, this is part of the driver, and this is again part of the driver. Okay. So driver is a piece of software, and they are written by the manufacturer of the device. If you have a camcorder, a camera, with the camera there is a camcorder controller, and the driver, of course, this camera controller is done by the manufacturer. This code is written by the manufacturer. So that when that device comes, okay, I install my controller to my PCI slot or ISA slot, and I install the driver to my operating system. And as you see, most of the time, drivers are part of the kernel space. They run in the kernel space. Some people don't like this idea. They say that, okay, I don't want to run somebody else's driver code in my kernel space. That's dangerous. That's too dangerous. And in fact, most of the Windows crashes are because of the faulty third-party device drivers. Okay, good. So I showed you this picture before. Okay, let's look at the details of the device drivers. Each I/O device is connected to each I/O device is attached to a computer. Okay, it needs some device specific code, and that code is called device driver. Device driver knows the details about the device, the controller and the physical operation of the whole device. Okay, usually nowadays we connect our peripheral devices using the USB port. Okay, so most of the time our device drivers are written already. Okay, and the USB controller is controlling them. Okay, so most of the time device drivers are, I mean, what kind of device can you have? I mean, either it's a external hard disk, external SSD device, external camera, etc. These are all standard devices, and we have nice drivers for most of them. Okay, so Windows has many device drivers available, thousands of device drivers available for these kind of USB devices. So most of the time manufacturers, they don't write any device drivers. They use the standard device driver code. Okay, so remember the code that I shown you before. I said that it uses memory mapped I/O to access the device registers. So to use those registers, you need the kernel privileges. That's why most of the time the device drivers are part of the operating system, and that is the cause of the major system crashes, because there are some buggy drivers. There are of course exceptions to this. For example, Minix 3, an experimental operating system. It is from the author of this book, Tannenbaum. Minix keeps the device drivers outside of the system kernel. Remember, Minix is a microkernel based operating system. It has only 10,000 lines of code in its kernel. Minix is not a small operating system. Its kernel is small, but operating system is not small because it keeps most of the stuff out of its kernel. So for Minix to have a system crash is more difficult than having a system crash for Windows. Okay, for Windows. Writing a device driver most of the time is defined by the operating system. Operating system says that what kind of a device are you? A block device or a character device? Block device means that like a disk or CD-ROMs. Remember our block transfers. Everything has to be transferred by the blocks, 1K, 2K, 4K blocks, or character drivers, keyboard or mouse. So you choose one of them, and the operating system will tell you you have to behave this and this and this way. Otherwise, I will not take your driver and I will not let you be part of my kernel. It does some checks. Okay, and that's kind of all I need to say about the device drivers. Of course, device drivers are complicated. There are, as I said before, there are thousands of device drivers available for Windows. And if you install a new device, Windows automatically goes to Windows servers and downloads the device driver if it is not available on your system. And that makes lots of I/O code for your operating system. Okay, good. Any questions? Okay, so what did we do up to now? We did this. We looked at the interrupt handlers. On top of it, we have the device drivers. Now we will move to more abstract level. Okay, we will do device independent operating system software. Okay, so whatever we do up to this point, it does not depend on the devices, and we need to provide this functionality. Okay, so device independent I/O software, they try to do something. Okay, something like this: uniform interfacing for device drivers. Doesn't matter what kind of device I have, interface should be uniform. Buffering is an important thing at this level. Error reporting should be done in a standard way. Okay, allocating and releasing dedicated devices should be done in device independent way, and providing a device independent block size again are the concerns for us at this level, device independent I/O software. Okay, if we have an operating system that says that whatever the disk driver you have, it should have a standard interface like this on part B. The task of the operating system would be much easier, right? So part B is a nicer picture for an operating system. Of course, that might make the device driver a little bit difficult to write because you have to have an interface defined by the operating system. Part A says that, okay, if you are the disk driver, your interface could be different depending on your hardware. Part B says that no, whatever your technology, doesn't matter if it's a USB or SCSI or serial ATA, doesn't matter. You have to behave this way. Okay. So for the operating systems we prefer this mode, the mode in the B. Okay. For each class of devices such as disk or printers, the operating system defines a set of functions. Okay, if you are a desk, okay, you need to give me a open function, an open function, a close function, a delete function, etc. Doesn't matter if it's a USB disk or CD-ROM. You need to give me these functions. Okay, each class of devices, they need to provide this kind of functionality. And often the driver holds a table. It says that, okay, internal I am using these functions, but for you, here is your table, and you may call any function you like from this table. And Unix does this a lot, and Unix says that, okay, I have this structure. There is a device directory in Unix at the root. There is a device directory, and each device has a file in there. Since it's a file, and inode is connected to that file, inside that inode, okay, you have information about the device driver. Also, you have information about the number of that unit. Number. This should be number. Number of that unit, because I may have more than one desk. So the major device number and the minor device number for the Unix is this. Major device number tells you, major device number kind of tells you the driver address. Minor is the unit number, and it is hidden inside the inode that is pointed by the files under the device directory. So Unix satisfies this uniform interfacing for device drivers this way. Good. Well, okay, it looks like I'm out of time. Are there any questions before I stop? Are there any questions? Okay, if there are no questions, then I will stop at this point, and I will upload these to the yesterday's and today's lecture on YouTube this afternoon. Yeah, unfortunately yesterday, uh, Higher Education Council announced that there will not be in-class face-to-face finals. All the finals has to be done either online or by projects or homeworks. And we are waiting for the university, okay, the president's office, to make a decision on how we do the finals. But it is not possible for us now to make a face-to-face final, in-class final. So we don't know. I mean, we are going to wait. But the Higher Education Council said that no face-to-face finals. But as you know, sometimes they change their mind and they say that no, it's okay. We don't know, so we are in a unknown situation. We will wait what the university says. I don't make those kind of decisions myself anymore. Okay, I will see you next week then.